Hi everybody, this is Dr. Nigro with the Chem Calculations screencast. This screencast is going to discuss how to use standard enthalpies of formation to calculate the enthalpy change for a reaction. All right, so we know that the formation of a compound from its elements requires an energy exchange, and it's either going to release or absorb energy. All right, if it releases energy, then the surroundings will increase in temperature. If it absorbs it, the surroundings will decrease in temperature. The amount of energy is known as the heat of formation. All right, and we represent that with the, not delta, sorry, HF. All right, I don't want you to confuse this with heat of fusion. This is heat of formation. All right, this O tells us that we're under standard conditions. So if we use these values to determine the change in enthalpy for a reaction, that reaction must also be under standard conditions. All right, now, how do we use those values? All right, well, the enthalpy change for a reaction under standard conditions is going to be equal to the sum of the amount of each entity and the heat of formation for the products minus the amount times the heat of formation for the reactants. All right, so remember that delta symbol means change in, and it's always final minus initial. So for a reaction, the final condition is the products, the initial condition is the reactants. So we need to look at those products and reactants, and we need to get their heats of formation values, and we need to add them up and then subtract the total reactants from the total products. All right, the N is if there is a coefficient in that balanced reaction. All right, let's say that we have 2 water molecules in the liquid state. All right, so we need to multiply the heat of formation times 2 for that one. All right, with that in mind, you need to watch out for your states. All right, it may take more energy to form a particular molecule in its gas state versus its liquid state versus its solid state. All right, so you need to make sure that when you write down your heat of formation, that you are writing down the one for the appropriate state for the reaction that you are looking at. All right, if it's an element, such as iron, such as magnesium, they have no heat of formation. All right, so you'll see some elements on your heat of formation table with zeros. That just means it's an element. All right, this includes the diatomic elements. All right, so if you see Cl2 and you go look for its heat of formation, you can't find it, that's because it's in its elemental state. It can't be formed, it just is. All right, the elements are the building blocks. If we take them and build a bigger molecule, then we have a formation. All right, but if it's just the element, it's not formed per se. All right, so we're going to try a couple of these. Right now, I've put a link at the top. If you have the PDF, you may not be able to access the link that way. However, on my Chem Calculations website, I did put a link in there as well. It's not the only table of standard enthalpies of formation. You can look anywhere on the internet. You're going to be able to find them. All right. So the way I tend to do it is I open up a table and I look up their values and I list them underneath each entity in my reaction. All right, so here I have 2 aluminum solids plus Fe2O3 solid forms Al2O3 solid plus 2 irons. All right, so aluminum is in its elemental state, so its heat of formation is 0. All right, if I go look for FtO3, I find its heat of formation is negative 824.2. All right, now my units for all of these are going to be kilojoules per mole, but rather than rewriting them, I'll just put it off to the side. All right, move across to the product side. For aluminum oxide, it's negative 1,657.7, and then iron's in its elemental state, so it's 0. All right, so those are my heats of formation value. All right, so now for my delta H of reaction under standard conditions, I'm going to start on the product side. I look at my aluminum oxide, I only have 1, so negative 1657.7. All right, kilojoules per mole, plus 0 for that iron, and then minus the reactant side, 0 for the aluminum, plus negative 824.2 kilojoules per mole. All right, I'm going to add the two together, or subtract them rather, and I'm going to end up with negative 833.5 kilojoules per mole. All right, so when this reaction runs, it should release 833.5 kilojoules for every mole that is reacted. All right, let's try this next one. So here we have magnesium hydroxide plus hydrochloric acid forms magnesium chloride plus water. All right, so let's again start with our heats of formation. All right, so I go look for magnesium hydroxide solid, and I find its heat of formation is negative 924.7. All right, and again, the units here are kilojoules per mole. All right, I go look for HCl aqueous, and it's negative 167.159. All right, I go look for magnesium chloride solid. It's negative 641.62. And then liquid water, negative 285.83. All right, so there are all my heats of formation values. All right, now I start setting up my reaction. All right, so I start on that product side. So I have 1 magnesium chloride, so negative 641.62, that's kilojoules per mole, plus 2 times negative 285.83 kilojoules per mole. All right, so there are my products minus my reactants. All right, so only 1 magnesium hydroxide, so negative 924.7, and then plus 2 times negative 167.159 kilojoules per mole. All right, so I take my reactants, or sorry, my products, 641.62 plus 2 times 285.83. All right, so I have a negative 1213.28 kilojoules per mole minus, and on my reactant side, 924.7 plus 2 times 167.159. Negative 1259.02 kilojoules per mole. All right. All right. When I take these two together, I get a positive 45.74 kilojoules per mole. All right, so in this case, when this reaction runs, it needs to absorb 45.74 kilojoules per mole of reaction. All right, we're going to do one more. All right, again, I'm going to do my heats of formation underneath my components. So for silicon tetrahydride, positive 34.3, and again, these are all kilojoules per mole. Oxygen's in its elemental state, so 0. Silicon dioxide is negative 910.70 kilojoules per mole. And then for gaseous water, negative 241.818 kilojoules per mole. All right, so there are my values. Delta H of the reaction under standard conditions. Start with the products, negative 910.70 kilojoules per mole, plus 2 times negative 241.818 kilojoules per mole. All right, so there are my products, minus those reactants, positive 34.3 kilojoules per mole, plus 0 for that oxygen. All right, so I add up those products and I get negative 1,394.3 kilojoules per mole minus positive 34.3 kilojoules per mole. All right, and in the end, the enthalpy change for the reaction is going to be negative 1,428.6 kilojoules per mole. All right, so this reaction is going to release 1,428.6 kilojoules for every mole of reaction. Okay, all right, so again, use the internet to find the values if you can't find them in your textbook or in your notes. And then it's products minus reactants. Don't forget, the state of matter is very important when you list the heat of formation, and that the coefficients in the balanced reaction need to be multiplied into that heat of formation so that you have the correct amount of energy for the correct amount of molecules that are being formed. Okay?